I think this morning we got through fairly seamlessly. I had a lecture yesterday where it didn't go off once. Look, everything, yeah, awesome. So let's consider the following matrix. I'll just call it matrix A. I'm going to try to make this relatively simple. It's -1, 2, -3, 4, 2, 1, 5, -2. Oops. Let me make this 4 by 4. Sorry. 4 and let's say 4 and 7 and 9 and 2. Okay, I have some matrix. I don't know where it came from. I don't know what it represents yet. That's actually going to come next chapter. This matrix absolutely comes from somewhere, and it's not a system of equations. It's something actually much higher level than that. The matrix describes something. Loosely, we'll say it's a transformation. Okay? It describes something taking place that we haven't learned yet. It's the next chapter. But I have a matrix in place, and I want to talk about the 4 fundamental subspaces of this matrix, because from that we're going to build an entire system of things. Okay? So what was the first one? What one should I find first? You guys remember? Because some of you did this on the previous quiz, even though I didn't ask for it. You actually did some extra stuff when you were solving one of the equations. Row space of A is probably the best thing to find, because if I find row space of A, then it actually makes the null space of A, I can piggyback off it, in a sense. Everybody got that? Or should I find the null space of A first and then use the row space of A, piggyback? Actually, do the null first. And then I can ignore the column of zeros. See, if I do the row first, I can't parameterize. So we'll start with the null. All routes are correct, but not all routes are efficient. The one thing I don't want you to do is to do the same problem twice. Because you chose to do the row space first, do the row operations, whittle it down. Now you do the null space. You found you did the exact same row operations, but now with an augmented, yeah. And that's extra work. So in order to find the null space, what we first thing we do is we say, and the reason I'm going square, last time I did this, I did it not square, so you could see where the dimensions ended up. But now that you have that, in application, you're pretty much always going to use square. Okay, there's not as much application for non-square. So I want to find all solutions to this. The solution space of this is a vector space itself, and it's called the null space. So this is, let me realize, this is A, this is X, this is the 0. So the way we're going to solve it is we are going to augment it. The reason we're going to augment it rather than, let's say, try to use an inverse or a determinant, what are my possibilities for the null space? I have 2 possibilities.
Either it's unique, it's just the trivial solution,
Or
an infinite.
it's either only the trivial solution, or there are non-trivial solutions, which now means there's infinitely many. Everybody okay with that? There's 1 or infinity. But there's always going to be at least the trivial solution. We know that x1, x2, x3, x4 equaling 0 is a solution. Is it the only solution, or are they non-trivial? If I try to solve this either using an inverse or Cramer's rule or some other way, there's nothing wrong with that. But if it turns out there's non-trivial solutions, I reach a dead end, because there is no inverse. Cramer's rule will produce 0 over 0 for each solution. So that's probably not a good way to go. What if you knew this had a unique solution? Then could you use the inverse or Cramer's rule? If it had a unique solution? Yeah. But you don't know this has a unique solution. So that's why it's kind of a waste of time going those routes, because, again, if this has non-trivial solutions, there is no inverse. That's one of the equivalent conditions.
Wait, if there's a unique solution, isn't it just the 0 vector?
Yes. But if that's the only solution, that's the only way an inverse exists. If there are non-trivial solutions, there's no inverse. But what's worse is, if there's non-trivial solutions, then I use Cramer's rule. There's 5 4x4 determinants, and they'd all be 0. Again, dead end. So I'm avoiding that way on the chance that maybe there is not a unique solution. There isn't. That would be a boring problem if there were. Right? That would be really boring. So let's do this. So I'm going to say it out loud, but I'm not going to write them down to save space. So let's take 2 row 1s and add it to row 2. Let's take 2 row 1s and add it to row 3. Hold on, so 2 of these added to this would be 12. I did that right. And let's take 4 row 1s and add it to row 3. 15, negative, so -3, and it'd be 18.
And the second one should
Did
be -2.
Did I screw it up? 2 of those.
No, like the first matrix you wrote from the original one.
Oh, did I? Good catch. That should be a -2, shouldn't it? Good catch. Oh. Okay, what, so that changes that to a what? To a 6? Does that look good? Oh, saved my bacon. By the way, I don't make errors on purpose. I make errors. But if you guys don't catch them, we get to the other end of the board and go, why isn't this working? I think I told you guys this story once. Oh my God. I was teaching a differential equations class, and on the last lecture of the class, this is not a joke. Start the problem on that board. I get to that board, and then I come out and said, does everyone have this? Can I erase? It actually takes, I'm back to this board, one problem. So I start on that board, about 45 minutes later I'm there, and I know, I go, this isn't gonna work. It's like playing chess. I can see a few moves ahead, and I'm like, this is not gonna work. And I'm like, you gotta be kidding me, it's not gonna work. You know, and I said, there's an error here somewhere, I have no idea. And when the student said, no, right at the beginning of the problem, right when you started it, he said the board wasn't completely erased, so there was a stray mark. And I think you thought it was a negative sign, so in the next step.
Oh my God.
And I went, when did you see that? They go, oh, right then. And you didn't say anything? They said, oh, you were on a roll. I didn't want to interrupt. So 45 minutes later, I said, guys, we're done. I went ahead and wrote up a solution on the computer and emailed it to people because there's no way I could have done the problem. I didn't have enough time left. You gotta be kidding. So when you see the error, please don't sit on it and hold it. No, I'm not on a roll. It's gonna be a crash and burn. So thank you, Shadi. That would have been awful. Yeah, never hold on to it because I'm the only one in the room that probably can't see it, by the way, because that's tunnel vision. But so now I have this, and what do you notice? Hopefully you notice something.
The last are multiples of each other.
Yeah, I got a lot of multiples. That makes it a little easier. So I'm going to do -2 of these. Let me go ahead and put the first row back up. So 0, 5, -1, 6, 0. -2 of these. And then -3 of these. Cool. Now what? Okay, I need to solve this. I have 4 unknowns, x1, x2, x3, x4. I have 2 non-zero rows, that means what?
2 parameters.
2 parameters. I know I have to parameterize, but I'm gonna have to have 2 parameters. Well, because I didn't put a 0 there, I really can pick any of these 3. It really, truly does not matter. Anybody got an idea? What do you think will make my life easier?
X2 and X4.
2 and 4 would probably be easier. How come 2 and 4?
Because there's a -1.
Because generally speaking, when I have a choice between 2 numbers and one of them is 1 and the other one isn't, always go with isn't. If you go with the 1, then you got to multiply by the reciprocal of the other one, and now everything's a fraction. If I choose these 2 as my parameters, then when I solve for this one, there's no fractions in my answer. Everybody cool with that? Then when I throw all 3 of those in, there's no fractions in my answer. 1 and -1 are just as good in the parameterization world. It's the non-1s that cause the issue. So I always want to use those coefficients. What if? What if I'd had a 0 in this position here? Then most of us probably would have picked these 2 because, again, they're the only columns that had multiple numbers. But 2, 3, and 4 all have multiple numbers. So all parameterizations are legal, not all parameterizations are efficient. And this is one of the things I remind people of. Technically, there's an infinite number of correct answers I can propose, but not all of them are easy to get to. Probably the safest and the easiest answer would be if we pick 2 and 4, because then we can do a parameterization that doesn't have any fractions. It's not that fractions are wrong, we just already know they're going to be a little bit harder to work with. So we will say, let x2 be s and let x4 be t. Now with that, let's start with x3. Then x3, if I throw it on the other side, what's x3? It's 5s plus 6t. Think about throwing it on the other side of the equals. And how about x1? I'm going to throw that on the other side of the equals. So, but x1 now is 2s minus 3 of these. I have to actually distribute. Plus 4t's. Because I just took the x1 and I threw it on the other side. So when I distribute this, what will I get?
Minus 13x minus 14t.
Oh, s. I'm sorry.
Yes,
I
sorry.
said x.
I did say x.
Negative 18 plus a negative 14. Does that look correct? Is that good? We will be able to check this in just a moment, by the way. So what we say is like this. Any vector, and this is the language I always use, any vector of the form I go out of my way to make sure my 5 doesn't look like an S, by the way. Now, any vector of this form. So if you replaced S and T with any real numbers, that would be a solution. We agree there's infinitely many solutions. Everything I've written is true and correct, but I can improve upon this answer by doing what? You think?
So question, is a particular solution like the plus c in an integral?
Not exactly, but hold that thought. It's not the same thing exactly. Yeah. Yep. A particular solution would be as if I give you an initial condition in an integral to find the plus c. That would be a particular solution as opposed to a general solution. But here, there's not going to be any particulars because I only have a homogeneous here. If I had numbers on this side, then I would have something else. Okay, so we all agree that at this point, factor out the s. So negative 13, 1, 5, 0, plus t, negative 14, 0, 6, 1. Everybody cool with that? Okay, I need to write the answer somewhere. I think I'm going to put it at the other end of the board. The easiest way to express the null space is not to write linear combinations, but just to express what are the vectors in its basis, which would be negative 13, 1, 5, 0. All right. And what was the other one?
Negative 14, 0, 6, 1.
Okay, this is my preferred way of expressing it because it's the least amount of writing that says absolutely everything I need. If I said give me a basis for the null space, you would say the set that includes those two vectors. I want the entire null space itself. Okay, now I need every conceivable linear combination. That's what the word span does. Span makes it into an entire vector space.
Is it nullity the span of that?
What is the nullity?
Isn't it the rank of the null space or the dimensions? Of
Yeah, so in this case, what is the nullity?
2.
2. The null space is the entire vector space. Nullity is its dimension, and dimension is defined as the number of elements in the basis, which is 2. Is this answer unique?
No.
Instead of negative 13, 1, 5, 0, I want negative 27, 1, 11, 1. Yeah. Any linear combination of these two could serve as a vector. Why these two? Because they were the first two. This is how I built the space. Why mess around with this? Just take this. Just run with this. Okay? I'm pretty sure I did it right. Pretty sure. Not at this level. Certainty. So what are we going to do? We're going to check. I never ask to see a check. I assume it's done. 13 plus 2 minus 15 plus 0, that's 0. Negative 26 plus 1 plus 25 plus 0. Negative 26 plus 6 plus 20, that's 0. Negative 52 plus 7 plus 45, that's 0. That's how you do the check. Okay, I'll leave the second one out. Everybody good with that? That's the null space. Is the row space sitting there waiting for me? Can anybody see the row space clearly, or do I need to do that one from scratch?
-1, 2, -3, 4.
See, if I was gonna do the row space, I'm just gonna do row operations on that and stop. And isn't that the last matrix I would get? Everyone sees that, I hope. So if I said do the row space, that's what you would do. That's why I'm saying you can read the row space in that answer. I think it's fairly safe to say that. So the row space would be the non-zero rows if I ignore the column of zeros. So -1, 2, -3, 4. And what's the other one? 0, 5. Did I write it correctly?
Yep.
Okay. The rank is 2, the nullity is 2, that adds up to 4, that's where the rows live originally, that has to be the case. If some reason I messed up somewhere and I have an extra row or something, it still has to add up to 4 no matter what I do. So if it doesn't add up to 4, I know I have an error. Now, we know what dot product is. Let's do the dot product between these two. So I get 13 plus 2 minus 15 plus 0, that's 0. Huh. I get 14 plus 0 minus 18 plus 4, that's also 0. Huh. 0 plus 5 minus 5 plus 0, that's also 0. And 0 plus 0 plus -6 plus 6. Wow. This is something way cooler. The span of this is an infinite number of vectors. The span of this is an infinite number of vectors. If I take any vector from this set and dot it with any vector of this set, I'm going to get 0, aren't I? Because you just basically said, take C1 of these plus C2 of these and dot it with C3 of these plus C4 of these. All the individual dot products would have produced zeros. That's an interesting thing, isn't it? I have a vector space where every vector in that space is orthogonal to every vector in the other space. And that's an absolute across the board, no exception. So what we do is we say, in this case, null space and row space are, the term is, orthogonal subspaces.
And this is always true?
The row space and the null space will always be orthogonal subspaces. We're going to talk about those terms in general in a moment. Orthogonal subspaces means every vector in one is orthogonal to every vector in the other, without any exception. What's special about this, though, is the dimension. What if I said, consider every linear combination of all of those guys? Would I get R4 back? Let me give you a simple picture. I took all the rulers back. I took them back between classes, you know, our vector rulers. Okay, so I have to use pen rulers today. All right, but we're in R3 for a moment. Let's say my null space is a linear combination of these two guys, and let's say my row space is this guy here. Here's what we now know. This guy is orthogonal to the plane that these guys live on. We know that. That's what that's saying. Okay? Now, if I look at this and I said, well, if I take any linear combination of the threesome, will I get every vector in R3? So I have two vectors. Keep it simple. Let's say two of the vectors are on the floor and the other one's on the z-axis, just to make it easier. I'm going to take these two vectors on the floor and the one on the z-axis. Well, then how do I get this vector here? Well, I take enough of that one plus that one, and then I take that one. In other words, I can get every vector in R3 because I can take every multiple of this vector to give me how high I want to be, and every combination of these guys to give me the x and y I need to get. Does that make sense? As long as the subspaces are orthogonal, I can generate everything. I generate everything without doing a lot of work. So if I put these two together, and the way we say it is like this. Let me give it a name. Let me call this vector space A and this vector space B. No, I don't want to be too clever here. I'm defining a new symbol, a plus sign with a circle around it. That literally means every linear combination of vectors in one, together with every linear combinations of vector in the other, I will now, remember, I had vectors on the plane. Linear combinations stay on the plane. I had a vector in the z direction, combinations stay in the z direction. But if I put the two together and consider every linear combination, didn't we get all of R3? What's this going to give us?
R4.
R4. Which means these four vectors will constitute a basis. Ooh. Let's suppose that I wanted to have an orthonormal basis. Well, it turns out this is the easiest kind of Gram-Schmidt problem. Do you know why this is an easy Gram-Schmidt problem? These guys are already orthogonal to these guys. I just need to make these two orthogonal to each other. I need to move one of them, and then I need to make these two orthogonal to each other. I only need to move one of them. In my example that I just did. These two are on the same plane. This is on an orthogonal plane. I only need to move one of these. You see it? Now that these two are orthogonal, they are already orthogonal to this guy. There's less work involved. Way less work. Otherwise, this would be a really long problem if I just gave you four random vectors. But because they're in what are called orthogonal subspaces to begin with, I only have to Gram-Schmidt them within their own subspace. This is something that will come up somewhat often in chapter 7. That's kind of cool. Now, I could say, let me take I have a vector, one vector on the floor, one vector only, and I have the vector in the z direction. Would they be orthogonal? Vector on the floor.
Yes.
Vector in the z direction. So would you say every multiple of the vector on the floor and every multiple of the vector here clearly would create a subspace? But what subspace would it be? My vector on the floor was pointing directly to me, okay? So what's the subspace? The plane that cuts through you. Are you in my subspace? No, only that direction. So did I get all of R3? No, I only got a two-dimensional subspace of R3. How come? Because I used that one vector and that one vector. I only got two vectors. I have two orthogonal subspaces. Every multiple of this vector is orthogonal to every multiple of this vector. So it's the same scenario, but I don't have enough vectors to form a whole vector space. So orthogonal subspaces do not necessarily form, or when put together, don't necessarily give you the big space. Does that make sense? If I give you a second vector on the floor, now they do. So here's another term. If I considered every vector okay, so let's say that I'm going to be generic here. I need them to be linearly independent. That does not mean they're a basis. In fact, there's no possibility they're a basis. In fact, they're never going to be a basis for Rn. They're just linearly independent. Those two vectors on top are linearly independent. Those two vectors on the bottom are linearly independent. Right? But the row space is not R4. It's a two-dimensional subspace of R4. I have a set of k linearly independent vectors in Rn. So k clearly is less than or equal to n. Let's suppose k is smaller than n. So it's a proper subset. There's another set T out there. Let me call T this set of vectors, for lack of a better name. How about V k plus 1 up to Vn? The rest of the vectors I need. Okay? I'm going to create T from S. T doesn't exist yet. I'm going to create T. I'm going to create T to be a set that has all the rest of the vectors I need. We're going to do that in a moment. Okay? I only have set S. Think of it in simple terms. I give you two vectors in R3. It's not all of R3, but I gave you two linearly independent vectors in R2. Excuse me, in R3 there. And I want to figure out a third vector so that every, or let's say it this way, that in words, every one of these vectors is orthogonal to every one of these vectors. I want to create it in such a way that not only are S and T orthogonal, but T is all the rest that I need. I just gave you an example, one vector on the floor, one vector up, it wasn't enough. Then we'd say T is equal to S, and we put a little perpendicular symbol. and this is pronounced S perp. I know it sounds made up, right? Like nullity, you know, it sounds like one of those little, you know, peanut butter cookies, right? Bring some nullities for snacks today. S perp. I'm starting with a set of linearly independent vectors, and I want to create a set where every single vector in my new set is orthogonal to every vector in my original set. If I do that, I will have a set of, it's an orthogonal subspace. But better than that, S with S perp will be Rn. I will actually get the entire subspace. I'm going to do a simple example with R3 because it's easier for us to conceptualize. Okay? Let's consider set S being the following two vectors. -1, 3, 2, and 2, 1, 4. The span of S is a vector space, but it is not R3. What is it?
Two-dimensional subspace of.
Good. I just want you guys to get used to the language. It's not the XY plane. It isn't R2. It's a two-dimensional subspace of R3. Okay, we all agree with that. So I want to create a new vector space. We'll call it vector space T. I want T to be, how about x1, x2, x3, such that, let's call this one V1, and let's call this one V2, and let's call this one W1. I don't know, lack of a better name. What do I want? I want V1.W1 to equal V2.W1 to equal 0. I want every conceivable vector that gives me a dot product of 0. Do you agree there will be an infinite number of possibilities? Hopefully you see that. You could probably just start figuring some out. Okay, I'm going to start with an easy one. 3, 1, 0. We'll dot with this guy 1. But so will 6, 2, 0, and 9, 3, 0. Okay, but I need one that also dots with that guy. Ooh, well, that's going to be a little trickier. So here's what we do. Let's set it up. Okay, so what do I want? I want, first of all, let me do the first dot product. So that'd be -x1 plus 3x2 plus 2x3 equal to 0. Agreed? And then let's do the second dot product. 2x1 plus x2 plus 4x3 equals 0. By the way, I did everything for A. Everything I did for A, we now know we can also do for A transpose. And then we find the null space of A transpose and the column space of A or the row space of A transpose. It's all the same stuff. I'm going to leave it out because it's not new information. It's just different vectors. Now that we know what that part is, I want to solve this using a matrix. Okay. So my matrix would look like this. What do you notice?
You'll have to parameterize.
These showed up as rows this time. Ah, you thought they were going to show up as columns, didn't you? And why do they have to show up as rows? Because I wouldn't get a dot product that had 3 things in it otherwise. Ah, okay. So now let's do it. I'm going to have to parameterize, yes. But it's the placement of the vectors in my matrix, they came in as rows. Most people would have automatically thought they'd be columns. No. Interestingly enough, I've been doing this for a long time. I'll have students tell me, that I heard or I saw it somewhere. Yet no one can ever actually identify. It's sort of like when you start something by saying, they say, who says? I've had more students than I can count on. No, vectors always have to be columns. Really? I work with vectors all the time. I'd say they show up as rows at least as many times as columns, if not more. In fact, a lot more actually. But you know, when I'm solving things, they often show up as columns, but they show up as rows here. Why? I didn't tell you they did. We just did it, and that's how they showed up. So let's solve this. So how? -1, 3, 2, 0. 2 of those, 2 of those, 2 of those. This is kind of ugly looking. I want to parameterize this. Yeah, I can put zeros, but it's too much work. Do I want either x2 or x3 to be t? No. I'm gonna pick x3, but I don't want it to be t. I don't want any fractions. What do I want it to be?
18?
70. Right idea, wrong number. 70. No, there's whatever the other number is. Oh, then 7x2 must be 56t, so x2 is negative 8t. There you go. That's how you avoid fractions. Could you have said t and then the other one be a fraction? Sure. But then it makes x1 even worse. Quick check, right? Negative 56 plus 50, okay, I know that works. Now when I'm finding my x1, x1's going to equal 3x2 plus 2x3, negative 24 plus 10, that's negative 10t. You with me? So it appears W1 is any vector of the form, where is it? Negative 10t, negative 8t, 7t, or t times negative 10, negative 8, positive 7. Could I have just as easily called this negative 7t? I picked 70. Could I have just as easily said negative 17? What would that have done to our answer?
Change it to negative.
Yeah, all the signs would have been different. Does that actually change your answer since t represents any real number? No. No, a negative 1 times a vector in terms of this wouldn't change it because it's still t times that. Yeah.
Doesn't that mean that zero is the zero vector is also a possible solution?
Yes.
Would that work though?
Would the zero vector, well, the zero vector dotted with either one of these would still give me 0, wouldn't it?
Or is it going to produce R3 when we add them?
Yeah, this is a subspace of R3, and the zero vector is clearly included in its span. This is a subspace of R3 if I take every linear combination, and the zero vector is included in its span because all the vectors are emanating from the origin. That's one way you can think about it. That's where they would, someone used the word intersection earlier. That would be a correct way of thinking about it. That's the one point they all share in common is the origin. And remember, they have to have the zero vector to be a vector space. So now I wanted to find t. So if S is these two vectors and that's all it is, then the span of S is a two-dimensional subspace of R3. We know that. So what do I want to call t? Do I want to call t the vector with parameters in it? Or do I want to call it just this part? No, I want to use just that part. Because now when I say the span of t, I have every multiple of t. Now, let's do a quick check. 10 minus 24 plus 14, that's 0. Negative 20, negative 8 plus 28, that's 0. So this is orthogonal to both. Therefore, every multiple of this is orthogonal to every linear combination of these. So t is now equal to S perp. Or you could say S is equal to T perp. It'd actually be the same thing. And now when I do the set addition, that's what we call this. When I do S, that means every linear combination of all of them simultaneously. Please don't confuse that with every linear combination of these guys, you're still on the same plane. Plus every linear combination of this guy, you're treating them as no, at the same time. Oh, so when I say I have two vectors on the floor and I have one going up the Z, I want linear combinations of all three simultaneously to get me all around the room. Not one or the other. Simultaneous. So this would equal now R3.
Yeah, is that just equal to the sum of all the linear combinations?
That's basically think of now, I have a new basis that includes this one, and this one at the same time.
You can also write it as a sum of the linear combinations if you want to make it long.
I'm sorry,
Can you also write that as a sum of the linear combinations?
yeah, this is easier.
Yeah, I'm just wondering.
Well, so is it the same thing as S, the union of S and T, of the span of the union of S and T?
That's a good way of thinking about it. What was our point here, though? We now know what an orthogonal subspaces are, but like I said, one vector on the floor, one vector up won't give me R3. So I needed to take the perp. I needed to create the orthogonal subspace that literally completed the vector space. Again, so what if I only gave you one vector on the floor? This is crazy, and I said this last day. I can start with one vector and generate an entire subspace. Whoa. That is complete insanity. Mr. Brown, you are completely out of control here. Yes, I am. Sometimes I go swimming 10 minutes after I eat. I mean, it's nuts. All right, I have a new set. 1, 2, 3. Okay. I have one vector in R3. The span of this vector is a line in R3. We know that. I want to generate all of R3. But I want to do it by creating an orthogonal subspace to that. Well, how do I do that? In a sense, I want to do something like this. Well, that's kind of weird. When I do this, I want every conceivable dot product, okay, that gives me the zero vector. Won't that mean in the end I'll have two parameters? In a sense, I should be able to create two vectors. So I want this plus this equals 0. I want this plus this plus this. Well, that's going to have a lot of solutions. Yes, I know that. You're generally not going to go 1 and go bigger, but you can. You're generally going to go bigger to smaller to complete it. Here's the idea. Oh, I'm going to do a problem that you've never seen before. I apologize for the fact that you've never seen this problem before. Let's start with something that's completely crazy. Let me start with a set of things in R3 that look like this. Okay? Let's see. You know how to prove this is a subspace by now? Okay. Can you give me a basis for the subspace at this point? Can you tell me the dimension of the subspace at this point? Can you give me an orthonormal basis of the subspace at this point? Yeah, that's what we did last time. Can you give me the orthogonal complement of this subspace at this point? See how good you guys are. Can you tell me a basis? Can you see a basis there without doing any work at all? This is where I'm hoping everybody's heading. Look at the coefficients of the s's first. What would it be?
2, 3, 1.
2, 3, 1. And the t's?
1, 0, minus 1.
1, 0, negative 1. W is the span of this set. We did a Gram-Schmidt process on the second vector last day to create an orthonormal basis of this set. Now what I'd like you to do is create the orthogonal complement of this set. Well, how the heck would I do that? That's what we just did over here. The exact same thing. So what you would do next would be do something like this. Do this and then solve. You're going to get a parameterized answer. So take the vector that you're taking the scalar multiples of. The span of that vector will be the orthogonal complement of this guy. It would be W perp, in other words. Could I now do the Gram-Schmidt process on that thing? Yeah, but I would only need to do it on the second vector. Why? Because this one would already be orthogonal to both of those anyway. I'm off the hook. Remember that? We talked about that before. Oh, no. By the way, is there more? Yeah. Are we learning more about this every time we look at it? Yeah, there's so much information in there. But the fact that I can build R3 from that by choosing the orthogonal complement. Okay? That's crazy stuff, isn't it? Now, I asked this question last time. In general, okay, when we started with a 4x4 and I asked for the null space and asked for the row space and we saw that there were orthogonal complements. I didn't have to do anything. It was given to me right there. But let's suppose between the two sets I didn't have 4 vectors. I could create another one by doing this process. That's cool. So in general, let's suppose I don't have enough vectors, okay? And I want to create. So if I'm in a higher dimension, I've got to do the algebra, do the matrix like we just did. We know how to do that. But what if I'm in R3 and I give you 2 vectors? And I want to create the orthogonal complement of those two. Somebody suggested something last day that you learned from Calc 3 called the what?
Cross product.
Cross product. So exactly what is cross product and what's it used for? This is exactly what cross product is. This is not the part that they ever explained to you. This isn't in any of the textbooks that I've ever seen. I've never heard an explanation. I just find it interesting. How many here are engineering bound? Okay, so cross product is probably really important because it's, you know, it's huge in physics. We do a lot of things in real life because we live in 3D and all that kind of stuff. But it's rarely, okay, never, explained what exactly is taking place. You know how to do it and how to physically get a vector, but what did you just find? And why did you do that thing you just did? That's the part that people don't talk about. So a number of years ago, and I don't say this jokingly, I was the person in class that asked why. When the instructor would say something, I'd say why. And more often than not, they couldn't actually answer it. No, this is the way you do it. Why? How do I know that that's going to work? How do I know this? It looks like you're just making it up on the spot. I'm sorry, but cross product always looked to me like someone just made it up on the spot. Hey, but I got answers, so it has to be valid. Yeah, but couldn't we have done it differently and got answers that were meaningful? So what cross product is, literally, is creating the orthogonal complement, but with a very, very specific goal in mind. So we're going to spend a few minutes on that. Some of the stuff I'm going to refer to the Canvas notes, just because it's a lot of writing. Those who were in my Calc 3 class, we did the same thing. Literally, when we're done with this, it's like the Matrix movie, right? It's just all the symbols running down the screen. You go blind. You can't tell what's going on anymore.
Never mind, I answered my question.
Okay, I love those questions. My favorite kind. So I'm going to take a set of vectors. Let's make it really simple. I'm going to take vector, let's call it vector v, oops, just v, and that's going to be v1, v2, v3, and vector w, w1, w2, w3. And I basically want the orthogonal complement of these two vectors. That's literally what I want to do. But the order that I do them, I'm going to count. The way I did it before, did the order matter? Because it was just two different rows of the matrix, it wouldn't have changed my parameterization. I would have got the same answer regardless of order. With cross product, we consider order to be relevant, okay, because there's direction involved. So I want a third vector, let's call it vector u, so that v dotted with u and w, sorry, dotted with u, both equal 0. Okay? Now, when I do this in Calc 3, this is not fun for me in Calc 3 when I do this. Because in Calc 3, I can't use a matrix. Sorry, I just can't. So in Calc 3, what I do is I write v1 u1 plus v2 u2 plus v3 u3 equals 0. And then w1 u1 plus w2 u2 plus w3 u3 equals 0. And then we solve for the u's. We treat the u's as the unknowns and the v's and w's. So what I do is I said, all right, let's take, let's see. Did I miss this? Okay, I want to take negative w3's times this, and then negative v2 times this. You see where this is going? We're going to use the addition method of baby algebra. And now I have negative v1 u1 w3, negative v2 u2 w3, negative v3. I probably should have written these in alphabetical order, but that's okay. And then I'm going to put here negative v2 u1 w, no, sorry, I can't read my own writing here. Negative v2 u1 w1, there we go. And then negative v2 u2 w2, and then negative v2 u3, oh, did I miss? That's a 3. Oh, you know, these should be 3's, my bad. I can't read my own writing. There we go. And then when I add them together, okay, this is why I hate doing it this way, sorry. One of them's got to be positive. Sorry about that. So we'll make this one positive. Then I add them, these guys cancel, and then I do the whole thing again. I hate doing it this way because God, it's so much algebra. Let's use a matrix. Can we use a matrix? Yeah, we're math folk. We're linear algebra. We're going to get the same answer. Man, it's not going to be such terrible algebra. This is what I do in the Calc 3. And those who were in my Calc 3, that's what we did. And it's hard to keep track of. But eventually we were able to do the whole thing and then solve and so on. So if I do it in matrix form, wait a minute, we just did this. Don't I just write that as one row, that as one row, then augment it with zeros? Oh, Yeah, that would be so much easier. Now when I do this process and I solve it, remember I'm solving for, oh, I'm sorry, these are, my bad, these are W's and not row. Sorry. U's are the things we're finding. Sorry about that. All right, so let me get rid of all this gobbledygook. So when I'm doing this problem here, I want to solve, I am going to parameterize in the end, am I not? I'm going to have a parameterized solution in the end. But what we generally do is we say, what's the simplest solution? Because multiples of that solution will still be a solution. So in a sense, we're parameterizing, but we're taking the basis vector. Okay, that's what we're actually doing. And so when all is said and done, okay, I'm going to save ourselves a little trouble, but we'd do the same thing. We'd say, all right, I'm going to take a certain multiple of this, add them together, get my zeros, do all that stuff. But what do we end up getting as a result? Does anyone remember? I'm going to show you the easy way, because I know you guys already know the answer. Okay, so what is in each position? This one's going to be what? Those are V's, sorry. So V2W3 minus V3W2. This is going to be V3W1. Sorry?
Wouldn't it be V3W?
Did I?
Oh, you said V2, sorry.
This is
Yeah.
right.
Yeah, sorry.
And then V1W3, and then the last one, V1W2 minus V2W1. When I solve this, I'm going to get T of these, T of these, and T of these. I skipped the parameterization part in the Calc 3 class because that's not something anybody in Calc 3 knows how to do, to parameterize a vector solution. But technically, my answer is going to be T of these, T of these, T of these. I want the basis of that answer, okay? And I show people that, the funny thing is, I laugh at how inefficient and bad people cross product. I've taught Calc 3 for a million years. At this point of the game in Calc 3, still 50% of all cross-product answers, like everything, is still wrong. We're more than halfway through a semester, and every time someone does a cross-product in my Calc 3, about 50% of all the answers are still wrong. But I've been doing this for years in physics because we're doing it incorrectly. I have people that try to do it by using a determinant when they don't know what a determinant is because they never learned that. A determinant cannot include a vector, it can only include scalars or scalar valued functions. And then they get the wrong numbers at every step of the way and the wrong signs all the way through. I said, no, there's actually a really easy way. That's it. I taught my Calc 3 instructor how to do that after I saw him do it the first time. I said, well, you know, there's an easier way. Because he kept getting the wrong answers. Now, how do you know your answer's right? This is huge. This is why I can't stand wrong answers in Calc 3. How do you know your answer's right? You take your answer and you dot it with one of the original vectors, and you either get 0 or you don't. If you don't, it's wrong. So I'm claiming that the answer is this. Oh, I'm going to write it out, right? And then so when I do the dot product, let me dot it with the first one. Then I'd have V1, V2, W3 minus V1, V3, W2 plus V2, V3, W1 minus V1, V2, W3 plus V1, V3, W2 minus V2, V3, W1. If I dot it with the original, this is what I get. That's the only way to know you did it right is you do the dot product. Remember, you're going to have numbers always. In linear algebra cross product, maybe the least important thing we ever do, and we're never going to look at it again. It's just an interesting application of finding an orthogonal subspace. Why don't we spend time on cross product in this class?
It's limited to 3D.
Yeah, it's limited to R3. See, finding an orthogonal subspace, I do this process, and I create a matrix and I solve it, but I can do that in every dimension. Cross product is only 3-dimensional, And we have an algorithm to produce the answer that's awesome, but that algorithm doesn't apply in higher dimensions. That's why knowing cross product isn't really necessary to do what we're doing, because we can still do it inefficiently. Now, I want to go back to the problem that we did earlier. I've erased it. Where I gave you the two vectors and we found the orthogonal subspace. Remember, I gave you two vectors in S and we found it. What were the two vectors again? Somebody tell me. In the order we found them, or in the order I gave them. It was like 15 minutes ago. I gave you two vectors and then we did the orthogonal complement and we found the W and we wrote it as a linear combination.
That was -1, 3, 2, and 2, 1, 4.
And what was our answer? It was T times what?
-10, -8, 7.
Now, my point was, it wouldn't have mattered what order we did this. We found our orthogonal complement. We were going to get that no matter what. What if I said, let's do the cross product of these? What would we get? 12 minus 2 is 10. 4 minus -4 is 8. -1 minus 6 is -7. What do you notice about your answer?
It's opposite, negative.
Well, it's a -1 times the first one. So on the line and space that these live, they're on the same line, aren't they? What if I had reversed the order of my cross product?
You would find that out the same.
I would have got the same answer. Cross product is not commutative, we know, because if I reverse the order, how do I know it's not commutative? Because if I reverse the order, I reverse the order of subtraction. Oh, so all my numbers would be the opposite sign. Orthogonal complement, doesn't matter what order you do things, you're going to get the same answer. So if I had done the same problem using cross product, I would have gotten T times this vector. Is T times this vector different than T times this vector? No, because T is any real number. So that's one of the really cool things. Cross product actually confirms your orthogonal complement answer. But orthogonal complement I can do in every dimension. That's why that's so much more powerful. But isn't it nice to know that the cross product that you've been doing all this time in other areas is consistent with what we're doing in all dimensions? Yes. Yeah, you would really hope that you don't get something weird and different. Now, cross product has its own unique properties. And the properties about cross product have to do with magnitudes and directions and things. And again, I'm speaking to the choir here, I know, because you guys have all had Calc 3 or in Calc 3 and you've done it. But if I take two vectors and I do the cross product between them, depending on which one's first, I'm either going to get this vector or I'm going to get this vector. But it's going to be in the same direction. I get a vector that is orthogonal to the plane that the first two vectors lived on. That's an absolute. What's not always the same is the magnitude. Oh, so in other words, the closer these are to a right angle, the greater the magnitude this is. The closer these are to parallel, the smaller. In fact, what if these are actually parallel? A vector crossed with itself is the zero vector, which means I now had zero magnitude. But how do I check that? Because the zero vector dotted with another vector is always the zero vector. There's always the number 0. So I do have consistency. So I'm going to show you something. Some cross product properties. Again, if you're in Calc 3, you've already seen this. This is on Canvas. I don't want you to take notes on this. It's too much. I jokingly say it's the Matrix movie. You know, there's just too much stuff going on. But I know you all know certain things. I'm going to go to that in just a moment. When I do a cross product, though, I do get a vector. But what vector am I getting? Well, I'm getting one that's orthogonal, but also its magnitude is really, really important to me. So let me talk you through it. Hold on. This is one of the nice things is I can do this. There we go. Let me turn the slide off. Okay, so the first thing is, okay, there's my answer. We just did this. And then we do a quick check always to see, do I get the zero vector? Okay. Now, I want to find the magnitude of the cross product. So no, that's the sum of the squares of the components, but that means I'm squaring this. So I square all these things. That's what that is. It's what it is. And you can't do it with numbers. You're trying to come up with a formula. You can't use specific values because then all you get is the value for those numbers. So after that step here, I say, now, I got that. Let's put it in our back pocket. Now what I want to do is, let's take the magnitude of u and square, the magnitude of u squared is just the sum of the squares. We know that's magnitude. The magnitude of v is the sum of its squares. Okay, great. And now I want to multiply those top two, and then I want to keep this one in my back pocket. Partly because in my magnitude of cross product, I just saw most of those terms, didn't I? Maybe I saw all those terms, I don't know. Let's double check. I got a whole bunch of terms where things are being squared. Now look back up here. Hey, wait a minute. 1, 2, 3, 4, 5. I have 6 terms that are the products of squares, don't I? Now let's go back to, sorry, where are we? Let's go back to here. What do I got? I got a whole bunch of terms, but I got more than 6. But the 6 that I have, well, you can actually see them on the line right here. Those 6 on that line, all of them are in there, but there's a few extras, aren't there? In fact, what are the extra ones? There's a few extra ones. That one, and that one are not on the top line. Keep that in mind. Okay? Now let's do the dot product of u and v. Well, that's the easiest one of all. U dot v is this. And then I want to square it. I'm squaring a trinomial. Yuck. All right, there's a lot of terms when I square the trinomial, but because I'm squaring it, some get added together. That's why you see some coefficients of 2. I'm happy with coefficients of 2. There were 9 terms, but 3 sets combined. Okay, now, what do I notice? Hey, those are the 3 other guys, aren't they? So now when all is said and done, if I take these guys here and I subtract these guys here, I get these guys here. That's why I don't do this by hand anymore, because I'd fill all this board up and you'd all be blind and your eyes would be pointing in every which direction. Does everyone see that? It's sitting right there in front of you. Again, if I take the squares of the magnitudes product and I subtract the dot product, I get exactly the magnitude of the cross product. Notice, and even the negatives where they appear on the 2's. So now we get to this line right here. So let's just stop there for a moment. That's an absolute mathematical statement. I'm showing you by taking all the pieces of the puzzle, and you can say, wow, cool. Now, let's go to the other version of dot product. Remember, u dot v in general, isn't it magnitude u, magnitude v, cosine theta? We know that. So if I take the square of this, then it's this, this, this. Let's go a step further. Then wouldn't that be, I'm doing the stuff that's easy. Wouldn't it be that? And now when I distribute, I get that. Okay, I see all that. So if I replace this with this, and then I replace it with this, right, and then I distribute, oh, but wait a minute, those other guys are going to then cancel, aren't they? This guy's going to cancel. So when all's said and done, I get this equals this, but since magnitude can't be negative, that's the proof in the derivation that the magnitude of the cross product is length u, length v, sine theta. Now, don't you think that's kind of interesting? Because dot product is length u, length v, cosine of theta, which could be negative. This is length u, length v, sine theta. And like I said before, the greater the angle between them, the bigger the sine of theta is. 90 would be the biggest angle I would want to see. When my angle is 90, I've maximized the value, haven't I? And then I can just literally take the product of the magnitudes at that point. But as the angle gets closer to 0, the cross product gets shorter and shorter and shorter. Eventually, it could be of length 0. Now, one of the reasons we find this one so helpful, again, baby algebra, baby geometry, whatever you want to call it. We know the area of the parallelogram is simply base times height. What if I didn't give you the height? What if I gave you A, B, and theta? B isn't the height, H is the height. Well, how do I find H? It's a SOHCAHTOA thing, isn't it?
Inverse sine.
So sine of theta is H over B. So wouldn't this just be B sine theta? So that means my area is what? A, B, sine theta. A lot of people forgot that. Now, Oh, did I mention this parallelogram wasn't formed by lengths? It was formed by two vectors. Two vectors uniquely determine a parallelogram. They also uniquely determine a triangle, if you want to do it that way. So what is A really? A is really a magnitude of a vector, isn't it? What is B really? It's really the magnitude of the vector. Therefore, what's the area of the parallelogram? The magnitude of the cross product. That's actually really important, geometrically as well as a calculus point of view. The magnitude of a cross product is equal to the area of the parallelogram the original two vectors determined. Isn't that cool? Now, what if the angle between them is at a right angle? Then my parallelogram actually becomes a rectangle, and I can just multiply the magnitudes and not worry about the angle. But as that angle gets smaller and smaller and smaller, that area does also. Now, I know that everybody's seen this in some capacity, but we don't always know how to work it. One of the things that we have as an advantage is because we have the matrix algebra in our back pocket, we can do certain things faster. But the algebra here is really the same. Okay? There's really nothing clever or complicated. This is something everybody's seen, but we're looking at it from a very different point of view today, because we're looking at cross product literally as a special case of finding an orthogonal complement of vectors. Finding an orthogonal complement when I give you two vectors in R3 is equivalent to finding the cross product. Now, I gave you two vectors in R3 and I asked you to find the orthogonal complement. What's faster, do you think? Doing the matrix and solving it, or just doing the cross product?
Cross product.
Probably just doing the cross product, because that's just arithmetic. That's not out, I'm just literally doing arithmetic. And because I can check it so easily. But if I want to express something in vector space form, then I need to take my cross product and realize that's a basis vector for the orthogonal complement. One of the reasons in the cross product, and this is never explained, when we do the cross product and we get these numbers, wouldn't any multiple of that also work in a sense? Because we talked about parametrization. When I solved that problem for the orthogonal complement, you had to parameterize. So every multiple of the vector would actually work. So why do we take a coefficient of 1? We don't. And I have a lot of people tell me that they've learned things this way. Oh, I was told to always just make your parameter equal to 1 and then you get an answer. No, that's incorrect. Because if you get to choose the value of your parameter, heck, choose 0 every time. Makes things easier. No, you don't get to choose the value of the parameter. It's not anything like that. It's you're choosing the basis vectors. Basis vectors don't have parameters. So if I give you two basis vectors and now every linear combination of those forms a particular vector space, it wasn't, well, I took a parameter of 1. No, I didn't use any parameters at all. What am I taking linear combinations of? So in the case of the cross product, think about it in terms of orthogonal complement. We wrote it as vector with a parameter in front. But it's the span of that vector. That vector is the important thing, and no matter how we do it, we were all going to come up with the same vector. Wouldn't even matter what order we did it in. We were all going to come up with the same basis vector. Cross product, we might have come up with the negative because we could have switched things. But it was still essentially the same vector, wasn't it? Okay? And it was the basis vector of the orthogonal complement. Now, again, we all know this. I have a unit, I have a vector pointing in that direction, a vector pointing in that direction. We know the cross product is going to point that way. Or is it going to point that way? How do I know which one it is? How in the world am I going to figure out which one it is?
Right hand rule.
Yeah, so if I go that one, cross with that one, it's that guy. But if I go that one, cross, I'm not that good. I know some of you might be able to do this, so what I do is this. That's why it's called the right-handed rule. And probably my favorite application, because I just saw it recently and I saw somebody break. Anybody here have to change their own tire recently? That's the worst thing in the world, because first of all, the people that put your tires on use power tools. So it's so tight. So you're out there with the lug wrench and you're cranking, you're cranking, you're cranking, and every human being who's ever changed a tire at some point has this horrible realization, oh my God, am I actually tightening it rather than loosening it because nothing's happening? Be honest, we've all had that thought, haven't we? But fear no more, you actually do know, because it's basically the right-hand rule. There's a formal scientific name for the right-hand rule. You're screwing on and off things. It's called
Lefty loosey right.
yeah, righty-tighty, lefty-loosey. Everybody know that one? It's technically that's not exactly, because in a circle, half the time you're going right, half the time you're going left. It's really clockwise, counterclockwise, but righty-tighty, lefty-loosey works. So you're doing your lug nuts. If I'm going this way, where's my force going? In. That's how you tighten the screw. So you untighten the screw the other way. You tighten things by turning it clockwise. You untighten things by turning counterclockwise. That's how it works. That's what righty-tighty, lefty-loosey actually means. So at the top, if I'm turning it to the right, that's clockwise. The problem is at the bottom, I'm really turning it to the left. But that's what it is. Now, child safety cap. Tell me about a child safety cap. I don't know why they call it a child safety cap. It's human safety cap.
You have to push in.
Yeah, it kind of violates that rule. See, righty-tighty, lefty-loosey is the natural way I'm applying the force. It's going in the, but the child safety cap is reverse threaded in a sense. You have to do things backwards. What would be the common sense approach isn't going to work. So when I want to tighten something, literally when I'm tightening the, aren't I kind of like almost leaning into it while I'm tightening it in a sense, don't I? Because all my force is going that way. You don't lean into it when you're unscrewing it. You're pulling on it when you're unscrewing it, literally. Because isn't there a point when you no longer have to use your lug nut, your wrench? You can use your fingers. You don't push on it while you're unscrewing it. You pull on it. That's the natural reaction because you want it to go with you. So the child safety cap, you're pushing on it while you're trying to unscrew it. It's all backwards, which is why I say it's the human safety cap, because adults can't figure it out either. So what I do is I usually just take something and just poke a hole in the middle and blunt force. Okay, we have basically covered everything we need to cover. We're not done with vectors, but we're very specifically done with these types of properties of vectors. So the next chapter, we're going to start incorporating vectors and matrices together. Literally, they're going to coexist in order to answer questions. Everything's going to involve matrix times vector and different things, talking about basis. The next chapter is absolutely critical. I can't give you simple application in the next chapter. It's theoretical, but it's not as abstract as chapter 4. But everything we do and we accomplish in the next chapter is the setup for chapter 7, which is what the entire course has been about from day 1. It's all about chapter 7. But it's the last piece of the puzzle that we need to master. And the algebra of chapter 6, most of the times, okay, there's a little bit with change of basis that gets kind of icky, you know, and you guys now know that's not your favorite thing, but somewhat unavoidable. Okay, let's go ahead and stop that. I'm